Hi, my name is Adar and I am a PhD student at the Technion under the supervision of Professor Amir Degani. Together we submitted a paper titled A Variable Rolling Sleep Model for a Conceptual Leg Shape to Increase Robustness of Uncertain Velocity on Unknown Terrain. So the SLR, the swing leg retraction, is a very common scheme to improve robustness on unknown rough terrain of the sleep model, the spring-loaded inverted pendulum with a constant leg length and leg stiffness. The controller is the leg angle during flight, and we use two sensors, two detection sensors, the touchdown and apex detection sensor. The swing leg retraction can keep a relative height above ground, which we term y relative, if we tweak the parameters correctly. And we care about y relative because keeping y relative improves long-term stability, as we have shown in previous papers. The function theta of t, the controller function, is sensitive, however, to initial horizontal velocities. So the first question we impose in our paper is whether modulating K, the stiffness, and R0, the free leg length, improve SLR to perturbations in the initial horizontal velocity. We call this variant of the sleep model the variable sleep. Yet, theory and reality alone, the problem is that controlling K and R0 is mechanically complicated in reality. So the suggestion we give in our paper is to use a passive and optimal leg shape. So what is the passive leg shape concept? Imagine you have a leg shape like this and it touches the ground in this orientation. So it has a certain stiffness and a free leg length. If it touches the ground with a ground level which is a bit lowered, then the orientation is different and it will have a different stiffness and a different leg length. So all in all, for each theta, for each orientation, the stiffness and leg length will be unique. K and R0 are now coupled with the leg angle, while we maintain one controller, which is the leg orientation. One note should be made that the shape induces rolling here, so we can no longer use the variable sleep model, but we need to tweak another model, which we call a rolling sleep, which will include the rolling motion. So, in fact, we have made an optimization problem to find the controller and the coupled parameters. The cost function, or the f-val, is defined as the deviation of apex from the desired y relative when we perturbate both the terrain and the initial horizontal velocities. So a glimpse on the results here, we can see the f value versus the initial height and the desired y relative. So we can see that the constant yet optimized sleep model will behave like this, will have a certain f value. For the variable sleep, we'll have f value which is much lower, but when we use the more realistic model of the rolling sleep, we'll have f value in between. So I remind you that the f value corresponds lower f values, corresponds to lower sensitivity to uncertain initial horizontal velocities on unknown terrain levels when reaching y relative. In future work, we would like to verify the results we've obtained in this paper, and we already began with a mechanical design and experiments. And here you can see our robot with a special leg shape obtained from the optimization in slow motion. Thank you very much for your attention.